In the previous video, we derived the slope of a curve at a point being dy dt over dx dt, meaning the first derivative of a set of parametric equations is given by this formula as long as dx dt does not equal to 0. We also took the time to derive our second derivative, and that is the derivative with respect to t of our first derivative divided by dx dt. In the following examples, we're going to practice applying those two formulas. So let's just practice a few of these. So we're asked to find the first and the second derivative. In other words, we're going to find the slope and concavity, if it's possible, at the given value of the parameter. So we're going to first do a lot of things. So we're going to find the xy coordinate at a given value of t. We're going to find the first and second derivative, meaning the slope and concavity. So I've given you the graph of the set of parametric equations, just so we can kind of see it. Looks like a half of a parabola. Right? So we want to find, first of all, the x and y coordinate at a given value of t. Well, how do we do that? Really easy. We're going to plug in 1. So we have x is the square root of 1, and we have y equals 3 times 1 minus 1, which is 2. So we have the ordered pair 1, 2. So now we're going to be asked to find the first derivative at that point. Right? So our first derivative, remember, is dy dt divided by dx dt. So we're going to find the derivative of 3t minus 1 with respect to t. And of course that is just 3. Then we're going to find the derivative of x with respect to t. So that's going to be 1/2 t to the negative 1/2. That's kind of ugly. So I'm just going to rewrite this a couple of times. So we're going to have 1 over t, 2 times the square root of t. And remember, dividing by a fraction is multiplying by its reciprocal. So that is going to be 6 times the square root of t. So that's our first derivative in general. Well, what happens when t is equal to 1? The slope at this point on the curve would be 6 times the square root of 1, which is 6. And I think that's a pretty reasonable answer. If I were to try to draw a tangent line at that point, not quite getting there, you can see that's a very steep slope, and positive 6 seems reasonable. We also should be able to see from the graph that there is a positive concavity. When we find the second derivative, it should coincide with that graph, telling us that the concavity is positive at the point 1, 2. Okay, so let's just practice that second derivative since it's a little bit different. So let's practice that second derivative. Okay, so I think it would help us if we just wrote down that formula again, that the second derivative is the derivative with respect to t of our first derivative divided by the derivative of x with respect to t. Right, so let's go back up to our first derivative. That was that. And so we need to find the derivative of 6 times the square root of t with respect to t. So the derivative of 6 times the square root of t, that's going to be 6 times 1/2 t to the negative 1/2. Then we're going to divide by the derivative of x with respect to t. And we kind of already did that once, right? Here was our derivative of x with respect to t. That's what we got. So let's just write that down again. So we have 1 over 2 times the square root of t. And again, I'm going to clean that up. So that's 3. So that's 3. That goes on the bottom. That's the square root of t over 1 over 2 square root of t. Again, if I divide by a fraction, I multiply by the reciprocal, and I'm going to get just 6. The second derivative is just positive 6. Concavity is positive. So, do I need to put in a value for x and y? No, because this is just a constant. So the second derivative is just a constant value of positive 6. That's all we need to do. Let's look at the second example. These are parametric equations of this ellipse. In a previous section, we practiced how to eliminate the parameter and showed how that would indeed give you an ellipse. That's the cool thing about parametric equations. An ellipse in terms of x and y, it's not a function. It fails the vertical line test. But when we put it in parametrics, we can do some neat things. So the first thing we're going to do is we're going to find the x and y coordinate when t is equal to negative 1/6. So we have x equals 2 times the sine of 2 pi times negative 1/6. My goodness, what is that? That is going to be the sine of negative pi over 3. So that's 2, and what is the sine of negative pi over 3? Think about that. Where is negative pi over 3? It's in the fourth quadrant, so you should know sine is negative in the fourth quadrant. Pi over 3, 60 degrees, reference angles. So you should get x is negative square root of 3. Okay, so now let's find the y value. We have the cosine of 2 pi times negative 1/6. So of course that's the cosine of negative pi over 3. So just like before, negative pi over 3 is in quadrant 4. Cosine is positive, and this is going to be positive 1/2. So we have the ordered pair negative square root of 3, positive 1/2. So on our graph, let's see, that's going to be, let's see, negative square root of 3, positive 1/2, got to be about right there. So what are we going to do? We're going to find the first derivative. What is the slope of that tangent line at that point? Well, if I'm looking at this, we should end up with a positive value if I do my calculus right. So remember, we're going to take the derivative of y with respect to t and the derivative of x with respect to t. Alright, so here's my y. How do you take the derivative of cosine? That's negative sine of 2 pi t multiplied by the derivative of your angle. Now remember, 2 pi is just a constant, it's just a number, times t, so we would have to then multiply this times 2 pi. Divided by the derivative of x with respect to t. So we're going to have that 2 because of that constant. The derivative of sine is cosine of the same angle. And then one more time, we've got to multiply by the derivative of my angle, which is 2 pi. Now the nice thing is that they both have a 2 pi and they reduce. So we're going to have negative sine, well let's see, negative 1/2 sine over cosine. We could just call that tangent if you wanted to, of 2 pi t. Well, that you're saying it might be negative, but my graph looks like it should be positive. Well, let's go ahead and see what happens if I let t equal to negative 1/6. So I have negative 1/2 times the tangent, and we've done this before, so what's it going to be? That's going to be negative pi over 3. Alright, so we knew what the cosine of negative pi over 3, we know what the sine of negative pi over 3, you should know what the tangent is. In quadrant 4, the tangent is negative. So we're going to have negative 1/2. Remember, tangent sine over cosine. We're going to get negative square root of 3. So that's going to be positive square root of 3 over 2. So that is the slope of the tangent line at the point, the x and y coordinate of negative 3 1/2. And that does match my graph, making it a positive slope. Well, can we find the second derivative? Okay, so we found the first derivative. Now let's find the second derivative. Okay, so again, the more times you write this, the more you will remember it. So we want to take the derivative with respect to t of our first derivative. Divided by the derivative of x with respect to t. Okay, so how do you take the derivative of tangent? That's going to be secant squared of your angle multiplied by that 2 pi. And no, I didn't forget my negative 1/2. Divided by, now it's not on my screen, but I believe we've already taken the derivative of x with respect to t. What was it? It had that 2 pi in it, had the 2, and then the derivative of sine, of course, is cosine. So again, we can reduce that out. We can kind of get that together. That's going to be negative 1/4, because that 2 and that 2 is going to end up in the denominator. And then we can just leave it like that if you wanted to. But you know what? I'm going to either turn it all into secants, and if I turn it into secants, if I brought that up there, that would make it a secant cubed, or I could bring this down here and make it 1 over cosine cubed. And I think that's what I'm going to do. So I'm going to have cosine cubed of 2 pi t. Now remember, that's my second derivative, but I want to evaluate it when t is negative 1/6. So I have negative 1 over 4 times the cosine of, remember 2 pi times negative 1/6 was negative pi over 3, and I need to cube that. So I have negative 1, 4, and then the cosine of negative pi over 3, remember, was 1/2. So that's 4 times 1/8. That's negative 1. 4 over 8 is 1/2. Dividing by a fraction, multiply by a reciprocal, is negative 2. So what does that tell you about the concavity at that given point? It says it's negative. And sure enough, it is concave down. The graph does verify the calculus.